Okay, so let's begin with problem 2.4 from Robert Wald's General Relativity. In this problem, he wants us, or in 4a, he wants us to show us that on any coordinate basis, the components of the commutator of two vector fields v and w are given by this expression right here. So let's go ahead and get started with showing that. So to start, we can write the commutator of v and w acting on some scalar function f. This is just going to make it easier to expand this and make sense of things. So for A, we have V and W acting on F, and so obviously this is just V of W acting on F minus W of V acting on F. Since V and W are, let's remind ourselves, vector fields, we can expand them in terms of components and their basis, which are going to be just the derivatives in this case. So we'll have something like v mu del mu w nu del nu on f minus w nu del nu v mu del mu on f. So now we can expand these derivatives in terms of the product rule. So we're going to get this v mu times, and there's going to be two terms in here. We're going to get one that's delta mu w nu delta nu f, plus we're going to get a term that's just w nu up front with both derivatives both derivatives acting on the f like this. Then we're going to have our minus our other term with the w nu up front, and same thing, there's going to be two terms here with the derivatives, so we'll have the first one like this, and the second one with v mu out front and the derivatives both acting on the scalar function f. Now, since the w and v are just components, and also the partial derivatives commute on the scalar function f, these last two terms, or the last term in either line, are going to cancel. And that's going to leave us with this. And also what I'm doing here is just renaming the dummy indices in the second term. So w nu turns, or yeah, like these nu's are going to become mu, and these mu's are going to become nu. So w mu del mu, oops, v nu del nu on f. So this essentially is, I actually should have switched the indices the other way, so we're going to quickly change all the nu's to mu's and vice versa. Okay, and now we can write these in terms of like the fraction derivatives, or like in that form at least, so it looks more like the problem. So let's go ahead with that. We get v nu d omega mu by dx nu, and then we're going to pull out the derivatives on the f, so we'll have minus w nu dv mu by dx nu with the del mu f out front. We can remind ourselves though that what we're calculating right now is this, the commutator of v and w acting on f, and what we really want here is the muth component of the commutator of v and w. So with that, we're going to drop the del mu f from the end, and we'll get something like this. which is what the problem had asked us to show. Note that there's an implicit sum over the repeated indices here. I think Wald actually writes the summation symbol in explicitly. But yeah, it's there. Okay, so for problem B, we're going to let these y's, y1 to n, be as in problem 3c now. So I put 3c here, and so the y1 to yn are these smooth vector fields on an n-dimensional manifold M. At each point, they form a basis of a tangent space, and then we have this relation. So at each point, we can expand the commutator, and we get this relation at the bottom. And what we want to do is show this relation right here. So to go ahead and start with this, let's just write that relation from 3b, I think it is, that we're going to use. Equals C gamma alpha beta y gamma. But remember, y gamma downstairs is a smooth vector field which forms a basis for the tangent space, so we can actually write this. So this is going to be a component times a basis, which is the derivative. Okay, so with this, let's rewrite our commutator. So we're going to get something like y beta y, oops, I'm already doing this backwards, y alpha y beta minus y beta y alpha. And if we do this in terms of like this notation, we're going to end up with something like this. Y alpha lambda del lambda y beta sigma del sigma minus the same term but with alpha and beta interchanged. I'm not going to write that term, it's over here though. Okay, so let's rewrite this a little bit now. So we have y alpha lambda, and then we're going to do the product rule with this derivative. So we're going to first have del lambda times y beta sigma del sigma plus the y beta sigma out front times del lambda del sigma, and again this is subtracted, or we subtract off another term with alpha and beta interchanged that I'm not actually going to write. Now with this, term 2 ends up canceling. Remember, these y's now are just components, and the partial derivatives are going to commute here. So the second term, actually it doesn't even matter if the partial derivatives commute because there's no alpha and beta in them, and they're not acting on anything yet, so forget that. But the y's, we can move them amongst each other however you like since they're components. So term 2 is going to cancel with term 2 from where alpha and beta are switched basically. And this is going to leave us with this. So now I'm just writing the kind of like invisible term in with alpha and beta switched from term 1. And remember, this is going to be equal to so now we're going to do some renaming of indices just to help keep me organized. So we're going to rename lambda to mu and sigma to lambda. So in this case, we end up with, I'm going to go down here a little bit, y mu alpha del mu y beta lambda minus y beta mu del mu y alpha lambda. I forgot my del lambdas at the end, I'm sorry. Let me just make sure I have everything correct. Del lambda minus 4. Now the idea here is that these del lambdas are actually going to go away because of the equality also having a del lambda at the end. We can just say the parts beforehand are equivalent. So let's now rewrite this without the del lambdas. So we're going to have something like this. C gamma alpha beta y gamma lambda y mu alpha del mu y beta lambda without the del now. Subtract y beta mu del mu y alpha lambda del, nope, not the del lambda. Okay. Now we're going to take this line and contract or multiply by this y lambda tau. And I just want to remind you guys that if we have something like y lambda tau times, let's say, lambda delta or something, this is going to give us a Kronecker delta over tau and delta. So we're doing this multiplication to essentially get a Kronecker delta out front here. So we're going to have, we're going to have C gamma alpha beta, and then this y times the y lambda tau is going to give us a delta gamma tau. And then on this side, we just write everything as is. And we have our y lambda tau on the right hand side here. Okay, so now this Kronecker delta evaluates and we end up getting C tau alpha beta. And this is going to be something like y mu alpha. We have del mu acting on y beta lambda times y lambda tau minus y beta mu del mu acting on y alpha lambda times y lambda tau. Now another little identity that I want to remind you guys of is that if we have a derivative operator acting on a and b, just our product rule, we end up getting del a b plus a del b. So that implies then that del a times b actually equals del ab minus a del b. So we're going to make use of that in our next simplification here. So we're going to write these derivatives in terms of derivatives of the y that they're acting on and this y lambda tau at the end. You'll see what I mean when I write it out explicitly. So instead now, we're going to write delta mu acting on y beta lambda and y lambda tau and subtract off y beta lambda times del mu of y tau lambda. That's term 1 only. And remember, the inside of this derivative is going to evaluate to a Kronecker delta, like I showed earlier. So that's just a constant inside the brackets, and this derivative evaluates to 0. And then we're also going to have the contributions of the second term here. So we have the y beta mu out front, and then we have a delta mu of both of these, y alpha lambda, y lambda tau, again, which is going to be a Kronecker delta and evaluate to 0, minus y alpha lambda del mu y lambda tau. Okay, so this is top term here is going to have a minus sign. We're going to have minus y mu alpha y beta lambda del mu y tau lambda plus double minus sign, so it cancels out, y mu beta y alpha lambda del mu y lambda tau. So we're going to interchange or rename some variables here again, just to keep things organized. So we're going to call tau sigma now, and lambda nu. So that's going to look like this. Let's also switch the order of the terms now. So we get y mu beta, put the positive term first, y nu alpha del mu y sigma nu minus y mu alpha y nu beta del mu y sigma nu. Now, on term 2, we're going to rename the dummy indices now, just to get things in the form most similar to the problem. So in this term, mu is going to become nu, and nu is going to become mu, and otherwise we'll just rewrite this. So y nu alpha del mu y sigma nu minus y nu alpha y mu beta delta nu y sigma mu. So that doesn't actually change anything other than the representation, how we're seeing it. That's what we actually have now. We've rewritten tau as sigma, so the left-hand side is going to be c sigma alpha beta equals y mu beta. Oops. Y nu alpha del mu y sigma nu minus y nu alpha y mu beta del mu y sigma mu. Okay, so we're getting very close now. We have a c sigma alpha beta, and so we're going to contract now with y alpha mu and y beta nu. I'm just writing these first so I don't forget. Alpha beta equals what am I doing? out of space here. We know this is the y sigma mu. I'll just write it like this. Okay. Now, we're going to have a delta alpha beta here. That's from this y and this y with the mu's. And then a delta alpha beta again. And this is going to be times delta mu y sigma nu. Delta alpha beta from the outer y's here. And delta alpha beta from those y's. And then we are left with our delta nu y sigma mu. Okay, so finally we can write our answer here. We have C sigma alpha beta y alpha mu y beta nu equals d by d x mu of y sigma nu minus d by dx nu of y sigma mu. And let's just make sure that this is actually what we were looking for. I'm pretty sure this is it. Let's bring this, oops, down to our answer. And we have, so the sum is implicit in my unsigned summation notation, so that side is correct with the C. Although we're using sigma instead of gamma. And then that means, yeah. If we renamed mu to nu here, which would be perfectly fine, then we would match this form exactly, so we are correct.